In this clip, we're going to prove two fundamental results about the determinant. First, that a matrix is invertible if and only if its determinant is non-zero. Second, that the determinant of a product is equal to the product of the determinants of those two factors. And so it turns out that these two results are so interconnected that you kind of have to prove them both at the same time. So the first step, so this is called a lemma. So a lemma is like a little baby theorem that really nobody cares about, but it kind of helps you prove a theorem that you do care about. And this just is going to be a sort of a first step, that if E is elementary, the determinant of E times B equals the determinant of E times the determinant of B. So this is a special case of the second theorem, and this is just corresponding to the case when E is an elementary matrix. And so I'm not going to go through this in any detail, but the reason why this is true is that we can compute the determinant of E for each case, each of the three types of elementary matrix. And then you just compare and you see that this is true by the row operation theorem that we did last time. So for example, if we have an elementary matrix that looks like 1, 0, 3, 0, 1, 0, 0, 0, 1. So this is an elementary matrix that came by doing the row operation where we've added 3 copies of row 3 to row 1. Well, you can see when I go to compute the determinant of this matrix right here, it's an upper triangular matrix. So it's just going to be the product of the diagonal here. And so this is going to be equal to the, it's just going to be equal to 1, which is the same as the determinant of the identity matrix, for example. So anyway, leaving that aside, let's look at the other two parts. So we'll do theorem 1 first now. So this is A is invertible if and only if it has a non-zero determinant. So this arrow goes both ways, so we have to prove a couple directions. Okay, well, to start with, let's look at the following. So if we let R be the reduced row echelon form of A, then R is going to look like, well, we took A and then we did a bunch of row operations to it, right? So it's going to look like a product of elementary matrices times A. So I did row operation 1 and then row operation 2 and then a bunch of other row operations until we finally got to the reduced row echelon form of A, right? Then if I apply the lemma, once for each of these elementary matrices, then what we see is that the determinant of R is equal to determinant of EK times, and then we've got the product of all these determinants. Okay, so now let's see. We know that none of the elementary matrices have determinant 0. So since none of those intermediate guys in between can be equal to 0 right here, then, well, we know that if we have a product of things equal to 0, the only way that can happen is one of those things equal to 0. So we have that the determinant of R is equal to 0 if and only if the determinant of A is equal to 0. Or equivalently, the determinant of A is non-zero if and only if the determinant of R is non-zero. Okay, but if the determinant of the reduced form of A is non-zero, then, well, what does the reduced row echelon form of a square matrix look like? It's either the identity or it has a row of zeros. But it can't have a row of zeros, because if it had a row of zeros, then by the triangular form computation, it would equal 0. So we know that R has no row of zeros. And if the reduced row echelon form has no row of zeros, then our theorem tells us that it has to be the case that R is the identity. And so we've just shown that A is row reducible to the identity, but we know from the characterization of invertibility theorem that this is equivalent to saying that A is invertible. And so all of these are equivalences. They go both ways. So we get both directions of the theorem at the same time. And we are done. Okay. So then let's go to theorem 2. So this is that the determinant of the product is equal to the product of the determinants. All right. Well, let's do this by cases. So in the first case, suppose A is invertible. All right, so if A is invertible, then we saw from our characterization of invertibility theorem that A looks like some product of elementary matrices. If we look at the determinant of A times B, then this is going to be the determinant of, and I'll use that expansion. Actually, you know what? Let me grab this guy and go make some more room for myself here. There we go. So the determinant of A is going, or determinant of A times B is the determinant of E1 times da 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 da, all these elementary guys times B. Okay, so I've just taken this guy and substituted it in right there. Then we can use the lemma to pull all these out. Okay. And then I can use the lemma again to put these all back together again. And now, this thing that I have inside the parentheses right here is none other than A. And so now I've gotten to the place that I wanted to get to, showing that the determinant of A times B is equal to the determinant of A times the determinant of B. Okay. What about the case when A is not invertible? All right, well, in this case, let's see. So then we know that AB is not invertible by the theorem that we had earlier that talked about the product of, the inverse of a product of matrices. Okay, so then the determinant of AB must be equal to 0 by the theorem that we just proved. And 0, it turns out, is secretly the same as 0 times determinant of B, because 0 times anything is 0. And I know that the determinant of A is 0 because A is singular. That's also by the first theorem. And now once again, I've gotten to the place where I want it to be. The determinant of A times B is equal to the determinant of A times the determinant of B. And all cases are finished, so we are done. The end.